guys, this is Ms. Dominiak, and Ralphie's here as well to help with the second part of the quantum mechanical model. So the thing to know about photons, so photons are a type of light, and they absorb discrete amounts of energy. And we call that a discrete amount, a quantum amount, which means they only absorb a certain amount. So this red line kind of represents what I mean by that. An atom will absorb like this much energy, or this much energy, but not these bits in between. It's like this staircase pattern, and each of that is called a quantum, so the bit between. So this is a quantum, that's a quantum, so there's discrete amounts. Sometimes we think about it like atoms absorb any amount of energy that there is, but that's because these bits are so small, like the differences between them. So if we make this really small, see this red line? It looks like a straight line, but it's actually that staircase. So that's just something to think about. Just like the last notes, this notes has a specific equation that we're going to be using. Let's put this here. So if we're talking about the energy of a photon, this E means energy. And then we have these two letters here, so we haven't seen this one before, but we know our Greek letter nu means frequency, so how many times that wave reaches the top, so in 1 second, so if it's going like this, those 2 times it goes to the top. So this other one, that looks like an H, I don't know why it looks like that, but it's Planck's constant. So it's just something that's always, 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 always this number. That's why it's a constant. So you're going to want to memorize this. It's 6.626 times 10 to the negative 34th joules times seconds. So that means it's joules and seconds both on the top. Remember, frequency is per second. So we've got joules times seconds and then divided by seconds, which gives us just joules left. So energy is measured in joules. So let's do a sample problem. So compare the energy of a photon in a microwave traveling with a frequency of 3.4 times 10 to the 9th hertz, that means per second, and a photon in an X-ray traveling with a frequency of 4.6 times 10 to the 18th hertz. Let's talk about what each of these means. Remember from last lesson, frequency means how many times that particle, or for this a photon, goes to the top of the wave. So this is saying 3,400,000,000,000 times. So this particle in a microwave is in 1 second traveling not only, 300 million meters, 300 million meters, but in that it's going to the top of its path this many times. So for 1 second it goes whoop up, I forgot that number, a lot of times, 3,400,000,000,000. The X-ray goes up even more times. Notice this is 10 to the 9th, that's 10 to the 18th. So the first thing we want to do is talk about what we have. So we're trying to find the energy of each of these and compare them. So let's first work with the microwave. We know that the microwave, for the formula, we're trying to find energy of the microwave photon. So what goes on this side? Well, we know Planck's we're trying to find energy, We know Planck's constant. There we go. 6.626 times 10 to the negative 34th joules times seconds. You will always, always, always plug that in for this H symbol. So here we go. And then the frequency is given to you right here. 3.4 times 10 to the 9th per second. Remember, hertz is how many times it happens per second. So it happens 3.4 times 10 to the 9th times per second. Is there anything that can cancel? Well, this is joules times seconds, and you're dividing by seconds. So that means your seconds can cancel. And then you just multiply straight across. So go ahead and get your calculator out, and you're going to do 6.626 e negative 34 times 3.4 e 9. There you go. Here's your energy of the microwave, 2.3 times 10 to the negative 24th joules. So let's talk about the energy of the X-ray. So same formula, because you're trying to find energy. You know Planck's constant, so instead of that H, here you go. And then your frequency is given to you. It's up here in the problem, 4.6 times 10 to the 18th hertz. So you plug that in. So here's the initial equation for the energy of the X-ray. Same thing, do we have stuff that cancels? Well, seconds is technically on the top, and this seconds is technically on the bottom because you're dividing per second. So those will cancel. And again, multiply straight across. 6.626 e negative 34 times 4.6 e 18 equals. What'd you get? Is it this? All right. So which of these has more energy? So the energy of what have blank, blank, blank more energy than the energy of what? Let's compare our exponents. Negative 24, negative 15. Which is bigger? Negative 15 is a bigger number, so our X-rays have more energy than our microwaves. So X-rays have, well, how much more energy than microwaves? To figure that out, we compare. Always put the bigger thing on top because you're saying have this much more. So the energy of the X-rays divided by the energy of the microwaves. We'll pull them and put them in the formula. So here's my energy of the X-rays, and I'm going to divide that by the energy of my microwaves. All right, how do we plug this into the calculator? And this is where you need to be really careful, and you have to use that E button when you're dividing with scientific notation. So 3.0, and then remember, instead of times 10 to the E, so 3.0 E negative 15 divided by 2.3 E negative 24. What'd you get? Did you get 1.3 times 10 to the 9th? So let's just talk about that. 1.3 times 10 to the 9th. So one little itty bitty photon, that little packet of energy, has, let's see, times 10 to the 9th, 1,300,000,000,000 times more energy than the energy of a microwave. That's a lot of energy more. All right, let's do another one. So a photon has 6.13 times 10 to the 21st joules of energy. Joules is the unit of energy. What is the frequency of this photon? So we're given energy. Here's our equation. We're given the energy, so this gets plugged in right here. Instead of E, you've got your energy. 6.13 times 10 to the negative 21st joules equals. So Planck's constant, so that's the constant. It's always that, and you're solving for frequency. So if you're trying to get frequency by itself, and it's currently being multiplied by Planck's constant, then the opposite function would be to divide by Planck's constant. Here we go. Anything that you have on the top and the bottom, you can cross out. Well, Planck's constant is on the top and the bottom. So that leaves just frequency on the right. But if you do something to the right, you have to do it to the left. There we go. Do we have anything that's the same top and bottom? Well, I've got joules here and joules there, so they're going to go. This gets typed into your calculator. 6.13 E negative 21 divided by, this bar means divide, 6.626 E negative 34. Notice we're going to be left with per seconds, because seconds is on the bottom, which is the same thing as hertz. So, see what you get on your calculator. All right, did you get 9.25 times 10 to the 12th per seconds? If you did, great. If not, call a teacher over and talk to her. You could also write this as 9.25 times 10 to the 12th hertz, because hertz and per seconds is the same thing. All right, another problem. And this is going to be the doozy one of the day, so get ready. 5.10 eV, those are electron volts, is required to excite an electron enough to remove it from a gold atom. 1 electron volt is equal to 1.60 times 10 to the negative 19th joules. What is the longest wavelength of light that could cause this? So we've never seen this EV before. So some of you guys might be thinking, that's it, I'm out, bye. But I promise you can solve this. There's going to be a few steps though. So let's write out what we know. We know we're talking about 1.5 electron volts. That's what's required. We want to know if that photon has 5.1 electron volts, how long could the wavelength be? Well, we also have this. We know that 1 electron volt is equal to 1.60 times 10 to the negative 19th joules. And joules is a unit that we're familiar with. So we can convert my 5.10 electron volts to joules. So remember this? Okay, go ahead and set it up. If you have EV on the top and what you're starting with, and that's not what you want, you need to put that on the bottom. Whatever you want goes on the top. Well, what unit do we know, have we seen before? Joules. All right, these two things need to technically be equal to 1. So, for these to be equal, how many electron volts and how many joules? Well, we're given in this equation here. So 1 electron volt, because I got that right here, is equal to, because these need to be the same, 1.60 times 10 to the 19th, negative 19th joules. Notice I kept my numbers matched to their corresponding unit. All right. What can cancel? Electron volts. I just have a 1 on the bottom. That doesn't do anything, so you multiply straight across. 5.10 times 1.60 e negative 19th, and joules is my unit left. So here is the energy required to excite an electron enough to gotta go. How does that get us to wavelength? Well, our energy is in this formula. We also have this formula that gives us our wavelength. We don't have any energy in this formula, but this is energy. I can plug it into the energy of the photon. We know Planck's constant. That'll give us frequency. Once you know frequency, you can plug it in over here. We know the speed of light, so we can solve for wavelength. So this is a multi-step problem. You just have to use both equations, and the go-between between these two problems is frequency. All right, so we've figured out that our energy is 8.61 times 10 to the negative 19th joules. We know Planck's constant. Let's solve for frequency. Same thing, divide by Planck's constant on the right, cancel out what can cancel, divide by Planck's constant on the left, cancel what can cancel, and then do the math. All right, did you do it in your calculator? If you didn't, make sure you do it and get it right. 1.23 times 10 to the 15th per seconds. That's the frequency. We can now use that to plug this into our frequency, because we know the speed of light, remember, 3.00 times 10 to the 8th meters per second, to find our lambda, or our wavelength. Okay, so let's plug in what we just solved for, which is frequency. There it is. We know the speed of light, it's always 3 times 10 to the 8th meters per second. We want wavelength by itself so we can know how many meters in that one, like between the crests of the photon. So divide both sides by your frequency. Starting over here, cancel what you can cancel. If you do it to the right, you have to do it to the left. So there we go, cancel what can cancel. Those units, the per seconds, are on the top and bottom, they're gone. So now you have 3.00 times 10 to the 8th divided by 1.23 times 10 to the 15th. Make sure you're using your E button, or else your calculator will think this 10 to the 15th is actually on the top of your fraction, and it's not. So I want you to freeze your computer and make sure you get the right answer that I get. Did you get 2.44 times 10 to the negative 7th meters? Okay. Here are some sample problems and the answers. So work through these and see if you get them right. If you get stuck on anything, call the teacher over. All right, see you later.